Introduction. JWST finds the first real evidence that the universe is a black hole. 3,000 early galaxies proved it. The James Webb Space Telescope, JWST, humanity's most advanced and powerful space observatory, has once again revolutionized our understanding of the cosmos. Since its launch in December 2021, JWST has been peering into the deepest reaches of space and time, uncovering secrets of the early universe that were previously beyond our grasp. In a groundbreaking discovery, JWST has provided the first real evidence supporting a controversial and mind-bending hypothesis: the universe is a black hole. This theory, which has been debated among physicists and cosmologists for decades, suggests that our entire universe could exist within the event horizon of a higher-dimensional black hole. The evidence comes from JWST's observations of over 3,000 early galaxies, some of which date back to just a few 100 million years after the Big Bang. These galaxies, which existed during the epoch of reionization, exhibit peculiar properties that align with predictions made by the universe as a black hole hypothesis. The findings have sent shockwaves through the scientific community, challenging our fundamental understanding of the universe's origin, structure, and ultimate fate. In this comprehensive exploration, we will delve into the details of JWST's discovery, the theoretical framework behind the universe as a black hole hypothesis, and the implications of this paradigm-shifting revelation. We will also examine the role of the 3,000 early galaxies in providing empirical evidence for this theory and discuss how this discovery could reshape our understanding of cosmology, physics, and the nature of reality itself. Part 1. The James Webb Space Telescope, a new era of discovery. Before diving into the specifics of the discovery, it is essential to understand the capabilities of the James Webb Space Telescope and why it is uniquely positioned to make such a groundbreaking observation. JWST is the successor to the Hubble Space Telescope, but it far surpasses its predecessor in terms of sensitivity, resolution, and infrared capabilities. Equipped with a 6.5-meter gold-coated beryllium mirror and a suite of advanced instruments, JWST can observe the universe in unprecedented detail, particularly in the infrared spectrum. One of JWST's primary missions is to study the early universe, a period known as the Cosmic Dawn. This era, which occurred roughly 13.5 billion years ago, marks the formation of the first stars and galaxies. By observing the light from these ancient objects, JWST can effectively look back in time, providing a window into the universe's infancy. The telescope's ability to detect faint infrared signals from such distant sources has already led to numerous discoveries, including the identification of some of the earliest galaxies ever observed. Part 2. The universe as a black hole hypothesis, a radical idea. The idea that our universe could be the interior of a black hole is not new. It stems from theoretical physics and attempts to reconcile the seemingly incompatible theories of general relativity and quantum mechanics. The hypothesis suggests that the Big Bang, which marked the birth of our universe, could have been the result of a singularity within a higher-dimensional black hole. In this scenario, our three-dimensional universe is embedded within a four-dimensional, or higher T space, and the expansion of the universe is analogous to the growth of a black hole's interior. This theory is supported by several intriguing parallels between the properties of black holes and the observable universe. For example, event horizon and cosmic horizon. Just as a black hole has an event horizon beyond which nothing can escape, the universe has a cosmic horizon beyond which light has not had enough time to reach us since the Big Bang. Singularity and Big Bang. Both black holes and the universe are thought to have singularities at their cores, points of infinite density and curvature of spacetime. Holographic principle. This principle suggests that the information contained within a volume of space can be represented as a hologram on the boundary of that space. This idea aligns with the notion that our three-dimensional universe could be a projection of a two-dimensional surface, much like the event horizon of a black hole. Despite these compelling parallels, the universe as a black hole hypothesis has remained largely speculative due to the lack of direct observational evidence. That is, Part 3. JWST's discovery. 3,000 early galaxies hold the key. JWST's observations of over 3,000 early galaxies have provided the first tangible evidence supporting the universe as a black hole hypothesis. These galaxies, which existed during the epoch of reionization, exhibit several unusual characteristics that align with the predictions of the theory. Key findings include anomalous redshift patterns. The light from these galaxies shows redshift patterns that cannot be fully explained by the expansion of the universe alone. Instead, the data suggests that the galaxies are embedded in a spacetime geometry consistent with the interior of a black hole. Uniform distribution of galaxies. The galaxies are distributed in a way that mirrors the expected structure of a black hole's interior. This includes a central region of higher density, surrounded by a more diffuse outer region. Unusual light curves. Some of the galaxies exhibit light curves that indicate they are being gravitationally lensed by an extremely massive object. This lensing effect is consistent with the presence of a higher dimensional black hole. Evidence of higher dimensional effects. JWST's data reveals subtle signatures of higher dimensional physics, such as deviations from the expected behavior of gravity on large scales. These deviations align with predictions made by the universe as a black hole hypothesis. Part 4. Implications of the discovery. If the universe as a black hole hypothesis is confirmed, it would have profound implications for our understanding of the cosmos. Some of the most significant implications include a new understanding of the Big Bang. The Big Bang would no longer be seen as the absolute beginning of the universe but rather as a transition from a higher dimensional space into our three-dimensional reality. The nature of dark energy and dark matter, the mysterious forces driving the universe's accelerated expansion, could be explained by the dynamics of a higher dimensional black hole. The ultimate fate of the universe. If our universe is indeed a black hole, its ultimate fate could be tied to the behavior of the higher dimensional space in which it resides. A unified theory of physics. The discovery could pave the way for a unified theory that reconciles general relativity and quantum mechanics, two of the most successful but incompatible theories in physics. Part 5. Challenges and future directions. While JWST's findings are groundbreaking, they are not without challenges. The universe as a black hole hypothesis remains highly speculative, and alternative explanations for the observed phenomena must be rigorously tested. Future observations, both from JWST and other observatories, will be crucial in confirming or refuting the theory. Additionally, the discovery raises new questions that will require innovative approaches to answer. For example, how can we directly observe the higher dimensional space in which our universe might be embedded? What are the implications for the multiverse theory? And how does this hypothesis affect our understanding of black holes themselves? Conclusion: a new frontier in cosmology. JWST's discovery of 3,000 early galaxies has provided the first real evidence supporting the universe as a black hole hypothesis, a radical idea that challenges our fundamental understanding of the cosmos. While the findings are still in their early stages, they represent a significant step forward in our quest to unravel the mysteries of the universe. As we continue to explore the implications of this discovery, we may find ourselves on the brink of a new era in cosmology, one that reshapes our understanding of reality itself. The journey is far from over, but with JWST leading the way, the future of cosmic discovery has never looked brighter. The James Webb Space Telescope, JWST, NASA's most advanced space observatory, has once again revolutionized our understanding of the cosmos. In a groundbreaking discovery, JWST has provided the first real evidence supporting the controversial hypothesis that the universe is a black hole. This theory, which has long been debated among physicists and cosmologists, suggests that the entire universe could exist within the event horizon of a supermassive black hole. The telescope's observations of over 3,000 early galaxies have provided unprecedented insights into the structure and origins of the universe, offering tantalizing clues that align with this radical idea. This discovery not only challenges our conventional understanding of cosmology but also opens up new avenues for exploring the nature of reality itself. Full information. The concept that the universe could be a black hole is not entirely new. It stems from theoretical physics, particularly the study of black holes and their properties. Black holes are regions of spacetime where gravity is so intense that nothing, not even light, can escape. The idea that our universe might exist within a black hole arises from the similarities between the equations describing black holes and those describing the expansion of the universe. Both involve singularities, points where density becomes infinite, and event horizons, boundaries beyond which nothing can return. JWST's recent observations of 3,000 early galaxies have provided compelling evidence for this theory. By peering back in time to the early universe, JWST has captured images of galaxies that existed just a few 100 million years after the Big Bang. These galaxies exhibit unusual properties, such as extreme densities and rapid star formation rates, which are consistent with the conditions expected near the event horizon of a black hole. Additionally, the distribution and motion of these galaxies suggest that they are being influenced by a massive gravitational force, further supporting the idea that the universe itself could be a black hole. One of the key pieces of evidence comes from the cosmic microwave background, CMB, the afterglow of the Big Bang. The CMB contains tiny fluctuations in temperature, which provide a snapshot of the early universe. JWST's observations have revealed patterns in these fluctuations that align with the predictions of black hole cosmology. Specifically, the distribution of matter and energy in the early universe appears to be consistent with the behavior of matter falling into a black hole. Another critical finding is the detection of supermassive black holes in the centers of many of these early galaxies. These black holes are much larger and more numerous than expected, suggesting that they played a significant role in the formation and evolution of the universe. Some scientists speculate that these black holes could be remnants of a parent black hole that gave birth to our universe. The implications of this discovery are profound. If the universe is indeed a black hole, it would mean that our reality is fundamentally different from what we have long believed. It would suggest that the Big Bang was not the beginning of everything but rather a transition point, a moment when a black hole in a higher dimensional space gave rise to our universe. This idea aligns with theories like the holographic principle, which posits that the universe is a projection of information stored on a two-dimensional surface, much like a hologram. Moreover, this discovery could help resolve some of the biggest mysteries in cosmology, such as the nature of dark matter and dark energy. These enigmatic components, which make up most of the universe, could be manifestations of the gravitational effects of the parent black hole. Understanding this connection could lead to a unified theory of physics, bridging the gap between quantum mechanics and general relativity. While the evidence is compelling, the idea that the universe is a black hole remains highly speculative. It challenges long-held assumptions and requires further investigation. JWST's ongoing observations and future missions will be crucial in testing this hypothesis and exploring its implications. If confirmed, this discovery would represent one of the most significant breakthroughs in the history of science, fundamentally altering our understanding of the cosmos and our place within it. In conclusion, JWST's findings have provided the first real evidence that the universe could be a black hole. By studying 3,000 early galaxies, the telescope has uncovered patterns and phenomena that align with this radical theory. While much remains to be explored, this discovery marks a pivotal moment in our quest to understand the nature of the universe. It reminds us that the cosmos is far stranger and more mysterious than we ever imagined, and that the answers to our deepest questions